Yeah, hi all. It's my pleasure to invite you to the IISc MSR seminar series today. Today's talk is in the area of causal discovery, and it addresses an interesting open problem on the lower bounds in causal discovery. This is an interesting extension, in fact, to another work presented at a similar IISc seminar a few months back by Karthik and Shanmugam. They had provided us with an upper bound, and this work is more on the lower bounds. This work is by Vibhor, Porwal, Piyush Srivastava from TIFR, and Gaurav Sinha from Adobe. And Vibhor has kindly joined us today for a talk on the same. Vibhor is a researcher with Adobe at Bangalore. Prior to that, he completed his BTech in computer science from IIT Kanpur. At Adobe, Vibhor works on problems spanning causality, machine learning, and algorithms. His work has resulted in paper submissions, patents, as well as technology transfer to products. He is presented at conferences like AIStat, Sigmod, and AAAI. And apart from causality, he also has interest in approximate query processing. You may feel free to contact him in case of any collaborations in these areas. And without further ado, let me welcome Vibhor for this talk. All yours, Vibhor. Go ahead.
Thanks so much, Rahul, for the introduction, and thank you for inviting me. Uh, I'll share my slides now. Okay. Hi, everyone. I'll be talking about interventional complexity of learning causal graphs. This is based on joint work with Piyush Srivastava and Gaurav Sinha and was presented at AIStats 2022. We also have some extensions to our AIStats paper. Okay. So first I'll define what is a causal graph. A causal graph represents the causal relations among the variables of a system. So a causal graph is represented as a DAG with the set of nodes V if the set of variables of the systems is V. And then H from U to V means that U is a direct cause of V. So let's take an example. Here we have three variables: age, medicine, and whether some particular disease is cured or not. So we can see that age affects what medicine someone takes as well as whether someone is cured or not. And determines whether medicine also determines whether someone is cured. So this can be represented as a causal graph in the form of a directed acyclic graph, as we can see here. Okay, so today I'll be focused on learning causal graphs, the problem of learning causal graphs, and this is important in several fields, including health science, molecular cell biology, and computational advertising. Okay, so so uh, using observational data, like just the data collecting data from a system, it is possible to learn a causal DAG only up to something called a Markov equivalence class that has undirected edges. So I'll later define exactly what is a Markov equivalence class, but it the point is that it has undirected edges, and to direct the edges, it is necessary to do something called interventions. So what is an intervention? An intervention on a variable V or a node V randomizes the distribution of V, and it removes the influence of the parents of V on V. So in this causal tag, we can see that if B is intervened on, then the distribution of V will be randomized and the edge from A to B will break as shown in the diagram. Okay, so let me just give an example why interventions are actually necessary for learning causal graphs.
Hi, Vibhor.
Yeah,
Sorry, can I ask questions in between? Or
sure. Yeah, please.
I just wanted to ask, does an intervention set the value of a variable to a particular value, or when you say randomizes the distribution of V, what do you mean by that?
Okay. So in so if you think of this do operator, right? So in this do operator, you can actually fix the value of a variable, but in for our setting it we can just think of setting it to a uniform distribution. So uh, if you are thinking of this do operator, then it fixes the value to a particular value. So it fixes the value of a variable to some particular value, but you can also think of this intervention as setting b to a to some distribution. So in this case, let's say a uniform distribution over its domain. So it
Okay.
okay,
Yeah.
and for our purpose that suffices. Like uh, yeah, in problems like finding the best intervention and all, we we may have to fix it to some value, but in this case we just want to randomize it. That is how interventions we define intervention on a particular node, and what it does is
In,
it removes the
un-
influence. Yeah.
right, right. I understand.
Okay. 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 So I was talking about
Yeah, just to anchor this in the in the example that you gave, this corresponds to like, so B would be like a medicine, and you're saying it's like a clinical trial where I would pick a medicine uniformly at
right,
random, fix
right.
one drug, and irrespective of the age, I'll not.
Yeah,
And then
yeah, exactly.
based on that, see how what the efficacy of the drug is.
Right.
What, and using that sort of quote unquote experiments, you want to infer the structure of this graph.
Yes, yes. So initially, so if we know the graph, then we can infer the efficacy. But
Right,
in case we don't know what is the direction of edge from A to C, A to B, and B to C, right? So
right,
using intervention now, our purpose would be to learn those directions.
correct. And like you will define this, but you're assuming that an undirected template is given to you.
Yes, yes. That is that I'll define it later. That is called a Markov equivalence class, and it has a well-defined structure, and it
Okay,
has undirected edges. Yeah.
correct.
So we assume that this observational data is given, and using that, it is possible to infer the correct Markov equivalence class. Okay. Okay. Now I'll give an example to illustrate why interventions are actually necessary even in simplest of cases. Okay, so consider the data set shown here with variables u and v. So variable v takes value 20 when u is 0, and variable v takes value 10 when u is 1, as we can see from the table. And let's say we are given infinite rows of the same. So now assume that we in this talk, I'll assume there are no unobserved variables. That this means that only the variables I show here are present in the system. Okay. Now, so we can see that u and v are correlated and want to determine whether u is the cause of v or v is the cause of u. That is whether the edge is from u to v or v to u, right? So clearly it is not possible just using observational data to say whether the direction of this edge should be from u to v or v to u. So the solution to infer this edge is we can do interventions. So what we can do is, let's say if we are able to fix u to a uniform distribution taking value 0 or taking value 1 with equal probability, then if we now see that U and V are still correlated, then we can infer that U is the cause of V, right? And if let's say it was not the case, then after setting U to uniform distribution, taking value 0 or 1, if we would have seen that U and V are independent, U and V become independent, then we would have known that U is not the cause of V, right? Or another thing could be to just fix the similarly to fix the uniform distribution, fix the distribution of V to a uniform distribution taking value 10 or 20. So if again we find that U and V are correlated, we infer that V is the cause of U. So in here I'm assuming there are no unobserved variables because so that either U is the cause of V or V is the cause of U. Like they are correlated. Okay,
Right.
so this
So,
okay, yeah.
so I'm guessing that if neither is the cause of the other and there's a third hidden variable that causes
Right.
both of them, you will not find correlation between the two, even when you set these fix U and V
Yeah,
to
yeah.
these.
Basically, we would need to do both the interventions to infer that there is a third variable, unobserved variable, which affects U and V, and none of them are the causes of the other.
Right. And do you need uniform as such, or would any
Uh,
function do?
so, okay, anything would do actually. So if we, uh, yeah, so yes, anything would do. So if we, let's say, make it something like it takes value 0 with probability 0.7 and 1 with probability 0.3, and then if we see that U and V are correlated, we can still infer that U is the cause of V. Otherwise, if we see that U and V are independent, we can say that uh, U is not the cause of V. Yeah.
Okay, thank
Okay. So okay. In general, intervention on a variable.
Hey,
Let's yeah.
let me just quickly ask this. So you are assuming like a perfect black box that that's able to determine independence, or
Yes. Yes.
that's not a. So you're not worried about independence testing and
Right.
errors and
Yeah.
those.
Yeah. No. No. I am assuming that the observational data is sort of infinite and noiseless.
Okay. And like again, maybe a slight digression, but let me just sort of ask this: are there works that look at this? Like, so of course, there's a huge literature on like independence testing or like
Yeah.
correlation, like testing and like sample efficiency of those. But has that been sort of like
Yeah.
considered
So
in conjunction
yeah,
with?
there are works in this learning independences from observational data. For example, this
No, no,
algorithm.
I'm asking like so that there are errors there, right? Like if
Yes.
it's finite sum, so like have there been works that say okay, even if there is error, I mean there's some error, but like some sort of, let's say, a kind of a guarantee for causal, like learning causal graphs using a pack guarantee for say independence testing.
Right. So if you mean that, let's say, can we learn a MEC in which each edge is correct with certain probability,
Right,
then I'm not aware of whether there is some work doing that. But
right,
there are algorithms like greedy equivalence search or PC algorithm which actually try to find MEC given some data, not but I'm not aware of what is their guarantee given there are some errors in the data set as well as finite sample is there.
right.
uh, so yeah, I'll check, but right now I'm not aware
No, no.
of.
Yeah, I was just wondering if you knew this of the. Thanks. Yeah.
Yeah, yeah. And even there are works in this interventional sample complexity. So later I'll also assume that even after doing an intervention, I'm getting an infinite sample. So then there are works in sample complexity of those as well. Okay. Uh, so this example illustrates the need for interventions to learn causal graphs even in simple settings like without any unobserved variables or infinite data. So now in general, intervention on a variable lets us orient all the edges that are incident on it. So I'll just define on the next slide that there are we can infer all the whether some edge is present between two variables or not, you just using observational data, but may not be able to infer their directions. But using intervention on a variable, we can at least know the direction of all the edges that are incident on it, as well as few more directions can be inferred using standard deduction rules called Meek rules, which I'll not discuss in this presentation. Okay, so as discussed earlier, using observational data, we can know the graph up to its MAC or Markov equivalence class. So what is a Markov equivalence class? A MEC is a partially directed graph that is it has some undirected edges, some directed edges that represents the set of causal DAGs capturing the observed data distribution. So what this means is uh, that any of the DAGs that have say exactly same conditional independences as the observed data distribution, then we say that that particular DAG captures the observed data distribution. So IMEC just represents this set of causal DAGs, all having same set of conditional independences as the observed data distribution. Okay, and how it so let's discuss now how the MEC, what is the structure of MEC. Okay, so MEC has the same skeleton as any of the tags it represents. This means the set of adjacencies are same, exactly same as any of the tags. Okay, and and the directed edge from U to V is present in an MEC if and only if it is present in all the DAGs that the MEC represents. Okay, so as an example, the MEC representing uh, these three graphs, where in the first graph the edge is from A to B and from B to C, and in the second B to A and C to B, and in the third B to A and B to C. So MEC representing these three set of graphs is A undirected edge B and B undirected edge C. This is because we can see that there is a graph with direction from B to A as well as A to B. And similarly, there is a graph with direction B to C as well as C to B. Therefore, the edge between A to B and B to C must be undirected in the MEC. Okay,
So
okay.
I guess the point of the example is that like A to C, that edge is not present in any of the the any DAG in this equivalence class. Is that
Yes, so what that means is given B, A
right?
and C will be independent. That can be inferred just using observational data.
Okay, and got it.
So this is the only independence that is being inferred in
Hmm.
the using the data. So so
Okay.
we can so right now just using observational data, we only know that there is an edge between A and B, there is an edge between B and C, but we
Uh-huh.
don't know the directions.
Okay.
Okay.
And can you also elaborate the last line on the previous slide with like
Yeah,
yeah,
yeah.
intervention lets us
I'll
learn all
I'll
ages that are yeah. So can you
right.
explain how the like for the two
Yeah.
variable case it makes
Hmm,
sense,
hmm, hmm.
but for general, can you explain why?
Yes. Okay. So for example, here these three variables are there, A, B, C,
Right.
and let's say we do an intervention on A.
Yes.
Okay. This means we set A's distribution to some uniform
Right.
distribution over its domain. Uh, then if we now see that, let's say the actual graph was this A to B. Okay.
Uh-huh.
So now if we see the correlation between A and B after intervening on A,
Right.
so let's look at all three cases now. So if A to B was there, then clearly A and B must be correlated even
Hmm.
after intervention on A. But when, so if the true graph was this second one, B to A and C to B, then after intervening on A, we have removed the influence of B.
Right.
Okay. So after intervening on we will see that A and B are independent.
Okay.
And again, in the third case, we will see that A and B are independent.
Yes, I guess like my kind of uh, yeah, maybe I'll just like stop bothering you, but like when there are multiple parents and it's a
Mhm.
sort of a more complicated setup, I wasn't not obvious to me as to like it could be that but I roughly see what you're saying. Once I intervene, at least for that variable, you're like effectively cutting off all parent edges.
Yes,
So
exactly.
something
Yeah,
that wasn't independent starts becoming independent. Okay. So whenever
right,
probably the idea is
right.
whenever this flip happens, that X and Y were not independent, but once I intervene on Y, they start becoming independent. I know that X was a parent of Y. So something like that holds. Okay.
Yeah, yeah, yeah. Even if we earlier didn't know whether X was a parent of Y, after intervening on Y, if we
Right.
see that they become independent,
Right.
then we can infer that X was a parent of Y.
Got it. Okay. So probably given that it's a DAG, you can like do this. Okay. Okay. Makes sense.
Yeah, and as you just said, this so after learning these edges incident on a particular variable,
Hmm.
given that it is a DAG, we may infer some more edges. Like there is no cycle, so we may infer some more edges, and there is. So I'll discuss later. There we can infer some more edges using something like if there are no. Okay, let me just come to the next slide first.
No, no, makes sense. Yeah. So
Yeah.
A goes to B, B goes to C. So you already know that C cannot go back to A.
Right. So yes, exactly, exactly. If let's say in the MEC there was an edge between A to C,
Right.
and like between A and C, not A to C, let's say, but and we already knew that there is an edge between A to B and B to C, then we
Right.
could have inferred directly that the edge must be from A to C and not from C to A.
Right. Right. Yeah.
Okay. Right. Okay.
Hi, Vibhor.
Yeah.
So I had a question here
Sure.
before you go to the next slide quickly. So you're saying, so I understand how to create the MEC from the set of causes. So you have some observed data.
Mhm.
From that, you're getting a set of causal DAGs that might explain that data. And
Right.
from that, you can create the MEC.
Yes.
But how do you create this set of causal DAGs that might explain the data in more complicated cases?
Uh, so okay. After I mean, uh, I so GES algorithm called GES tries to do that, but the idea is that if you look at all the conditional independences in the observed data, okay, and then you can at least infer the skeleton. Skeleton means all the adjacencies, right? And
I
uh,
there are good efficient algorithms to do that. Like
I don't think there are efficient algorithms but it can be inferred using observational data.
okay, thank you. Yeah,
So yeah, I think GS is a greedy algorithm, and in general, in learning the MEC, I think is NP hard. In
Vibhor,
yeah.
to add to that question, So you said we could learn like a set of graphs, possible graphs that explain the data. But you're saying like in some cases we might be able to get the direction as well. Like
Yes, yes,
when is that possible?
right, right. So, okay, let's consider a simple example. I'll discuss this later, but let's consider this example. B, the edges from B to A and C to A. Okay. Then if you see that uh, B and C are independent, just using observational data, what can be inferred? Let's see. So we can see that B and C are independent, but given given A, B and C become dependent. Okay, so this special kind of thing can happen only when there is this V, something called V structure. So these edges can be inferred directly using observational data. Such kind of induced subgraphs can be inferred just using observational data because they they imply some special independences, conditional independences. So this wouldn't happen in any other case. In, let's say, just for now involving three variables. So if you see that B and C are independent, but given the other variable A, they become dependent, then the directions must be like this.
Uh-huh.
So
Collider, like, okay.
yeah, this is called a unshielded collider as well. So for example, in this case, uh, let's say we look at first and third variable, given given the uh, middle variable B, E and C are actually independent. But in the unshielded collider or this V structure case, we can directly infer that the edges from B to A and C to A because when we check the so when we because we can just using observational data infer that B and C are dependent given A. So this only happens when there is a
Yeah, yeah.
V
Okay.
structure. So these edges can be inferred just using observational data. Okay, right. So now we discussed why interventions are necessary, but in general, interventions can be costly because we are randomizing some variable of the system and that may be costly. And therefore, natural question is to find the minimum number of interventions required to learn all edges of a causal DAG. So for example, uh, we have the we have learned the MEC on the left using observational data. Okay, and by learning the MEC, I just mean we have these adjacencies. Okay, and using interventions, we can learn this true DAG, which is the actual causal DAG that we want to learn. So one may ask the question that what is the smallest set of interventions that that we need to learn all the edges of the causal DAG on the right. Okay. So as an example, if we intervene on B, C, and D, we can learn all the directions because as discussed, we can know all the directions of all the incident edges after intervening on a variable. So BCD is a set of interventions that can learn the DAG on the right. But the question now is uh, question now is for a causal DAG, what is the smallest set of interventions one needs to do to learn all the edges present in all the directions of edges present in the causal DAG? Okay, so now just to again define V structure. A V structure in a DAG is an induced subgraph of the form B to A and C to A, and B and C are not adjacent. Right. Okay, so it is well known that lower and upper bounds on the number of interventions for learning DAGs without V structures generalize to arbitrary DAGs. Therefore, from now on, I'll assume that there is no V structure in in our causal DAG, that in the given causal DAG, right? So I'll just focus on DAGs without V structures. So a V structure is an induced subgraph of this form, and I'll assume that this subgraph, this induced subgraph, is not present in our input DAG, because we can obtain lower and upper bounds by. So if we know the lower and upper bounds for DAGs without V structures, we can obtain such lower bounds for general graphs as well, general DAGs as well.
Hi, Vibhor.
Yeah.
What kind of interventions would be required? Like, I'm just probably asking a question that you'll come to, but would you intervene on all three of BCD at the same time, or B and
Okay.
then C?
Yeah. Yeah. Good question. Uh, so in most of the talk, I'll only consider single node interventions. That is, we intervene on B and then later intervene on C and then intervene on D. So it is possible to actually do simultaneous randomizations of nodes. So for example, one can randomize B and C together and collect data. So what does randomizing B and C together would mean? It means it would break the edges from of the parents from B as well as parents of C. Okay, so that is
So here we
possible.
are interventions.
But sorry.
Here we are considering only atomic interventions or
Yeah, yeah.
interventions.
These single node interventions are called atomic interventions as well. And and in most of the talk, I'll only focus on atomic interventions. So fine, in the last part, I'll also discuss about these multi-node interventions that simultaneously randomize on more than one node. But from but I'll tell when I'll focus on multi-node interventions. For now, I am just discussing about single node interventions or atomic interventions.
Thank
Okay.
you.
Yeah. Okay. So now coming to uh, main main results of our paper, main result of our paper, which is a universal lower bound. So this universal lower bound was introduced in a paper by Squares et al. In Europe's 2020. So what do we mean by universal lower bound? So a universal lower bound of L interventions for a MEC means that if an intervention set I is of size less than L, then for any ground truth DAG in the MEC, I will fail to fully orient the MEC. Okay. Um, so if let's say uh, there is a lower bound of L interventions, universal lower bound of L interventions, then even if we uh, even if we are given a DAG and 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 someone asks us to give an intervention set that that will orient the that will learn the edges of this DAG starting from its MEC, even then this uh, size L interventions would be required. So okay. So it is two main properties. It The low bound is applicable to all DAGs in the MEC. So MEC has represents some set of DAGs, and it this lower bound is applicable to all the DAGs that the MEC represents. And the lower bound is independent of the method by which the intervention set was obtained. So it could have been obtained by something called active algorithm or a passive algorithm, or even if we know the DAG, as I said, even if we know the DAG and So any even lucky guesses are applicable here. So somebody may guess a intervention set and and even then if it is of size less than L, the DAG won't be fully oriented. Okay,
So
so
it is like a forgiving notion because you're saying for any ground, like in the sense the universal refers to this fact that it's saying that even if you have the best possible DAG in this MEC, you will still need L interventions to orient. Is that's the point?
right, right. So okay, let's see.
Not
Uh,
a worst case kind of saying. It's not saying the worst. Like in this
yes,
MEC,
yes,
the
exactly.
worst possible DAG requires these many. It's saying
Yes, yeah,
every
yeah.
DAG in this requires L
Right,
intervention.
right. Even so, let's say if you give a intervention set of size less than L,
Hmm.
and then that intervention set, no matter what is the intervention set, you can take all subset of nodes of size less than L,
Right.
and then any of the DAG won't be learned in the MEC.
Okay.
Exactly. Yeah. And there are lower bounds for this worst case. Uh, so they say something like if you so this a low bound, a worst case low bound would be something like uh, there is a DAG on which this many number of interventions are required starting from the MEC. So something like that. But here, this lower bound of universal lower bound would be applicable to all the DAGs in the MEC. Even let's say something like a best DAG or something. Okay. So in this work, we address the problem of obtaining tight universal low bounds. I'll discuss what do I mean by tight here. Okay, so coming to the result of Squires et al., they prove that at least omega by 2 interventions are necessary to learn the directions of all edges of a causal DAG. Here, of course, we are, as I said earlier, I'm only focusing on DAGs which do not have any V structures. And here omega is the size of the maximum clique in the graph, in the DAG. So they prove that at least this floor of omega by 2 interventions, single node interventions are necessary to learn the direction of all edges of a causal DAG. Okay, now in our work, we improve this lower bound to n minus ceiling of n minus r by 2 interventions. So here I say improving. So we actually prove that this quantity is always larger than omega by 2. Here r is the n is the number of nodes in the DAG without V structure, in any DAG without V structure, and r is the number of maximal cliques in the DAG. Okay, so this we prove that n minus r is greater than or equal to omega minus 1. This would imply that our lower bound is always more than or equal to omega by 2. R is the number of maximal cliques and n is the number of nodes. Okay.
Maximal, not
Yeah,
maximum.
yeah, maximal. Yes. So this omega is the size of the maximum clique and this
Right.
R is the number of maximal cliques. Yes.
Correct.
Okay. Now I'll discuss some graph theoretic definitions that we need for a main technical contribution. Okay, so let T is a DAG without V structures with n nodes and R the number of maximal cliques in D.
So,
Okay.
Vibhor, when you say V structure, that is with respect to edge directions, right? As in,
Yes. Yes.
um, with the like in an undirected sense, you could have like a vertex B that's connected to vertex A and C that are like without the edge, you could have a V, but and the edges could be just like directed as a path, say. So that is
Okay.
allowed.
So the thing is, in the MEC you are talking about, there can be V structures, and what what the in what is known in literature is that we can. So let's say there are some directed edges in the MEC.
Right.
Then we can, after removing those directed edges, we obtain components. We obtain connected components which are all undirected.
Hmm.
Those undirected components,
Hmm.
if we orient them, they must be DAGs without V structures.
Okay. Okay.
Okay, and so it is known that intervention on one connected component won't have any effect on another component.
Right. Right. Okay.
So we can treat these
Hmm.
connected components independently, and orienting them, we get a DAG without V structures. So
Hmm.
therefore, it is okay to just consider DAG without V structures, and the lower bound or upper bounds generalize to those arbitrary DAGs.
Hmm.
And yeah, just one more thing to know, that this connected component, undirected connected component, is caudal. Caudal means there is no induced cycle of length greater than 3, or any cycle of length greater than 3 has a chord. So
Hmm.
those so this means the skeleton of DAGs without V structures have nice structure. They
Okay.
are caudal. So skeleton of DAGs without V structures are caudal, and skeleton of DAGs without V structures are also their MEC.
Hmm.
Right. Okay. So now I have a DAG without V structures, and R is the number of maximal cliques in that DAG. Now I'll define something called maximal clique sync nodes. So let's consider a maximal clique C, then the node with no outgoing edges in the induced subgraph DC. So DC is the induced subgraph restricted to the set of nodes C. C is a maximal clique. So the node with no outgoing edges in DC is called the maximal clique sync node, corresponding to the maximal clique C. Okay. So okay, consider the DAG shown here. It has maximal cliques AB, BCE, and CDF. Okay. So in the maximal clique AB, B is in the induced subgraph DAB, which is the for if we consider just the induced subgraph restricted to set of nodes A comma B, which is a maximal clique, then the node with no outgoing edges in this induced subgraph is B. Therefore, B is a maximal clique sync node corresponding to the maximal clique AB. Similarly, for this maximal clique BCE, E is the node with no outgoing edges in the induced subgraph BCE. Therefore, it is it is a maximal clique sync node corresponding to BCE. And similarly, F is the maximal clique sync node corresponding to CDF. Okay, now we also prove that for DAGs without V structures, there is an unique node uh, corresponding to a maximal clique, which is its maximal clique sync node. So this means no two maximal cliques have a common maximal clique sync node. Okay, this means that the number of maximal clique sync nodes is R. R is also the number of maximal cliques, right? So I'll I'll refer to in the subsequent part of the talk. I'll refer to maximal clique sync nodes as just sync nodes. Okay. So there are R sync nodes, and each maximal clique has a corresponding unique sync node. Okay. Okay. So now I'll define something called blocks in topological orderings of DAGs without V structures. Okay. So we have a DAG D, which is without V structures, and let sigma is a topological ordering of D. So the set of nodes, sorry.
Sorry, I had a question, probably very basic. I'm sorry for that. But the cliques that you're considering are on the MEC, which is the undirected graph. But here you're considering the directed graph and the sync node in that directed graph, is it?
Yes. So cliques, actually the maximal cliques would be same in MEC, which is just the skeleton of this DAG. So
I
the set of maximal cliques would be same, but the sync nodes would depend on the actual directions,
yes,
right?
yes.
So if, for example, in this particular DAG, if we consider the MEC and change the direction of this edge B to B to A, then A would be a sync node, and A is not a sync node in this particular DAG.
So effectively, you're saying the cliques in this and the MEC are the same. So yeah, that answers it.
Yeah, yeah. Cliques are same. Maximal cliques are exactly same. Yeah,
Thank you.
yeah. But sync nodes depend on the actual DAG because they basically are using, they are depending on the directions, right? The node with no outgoing edges.
Hey, Vibhor, like, explain to me one thing before you go on. So if I look at a MEC, like an undirected graph, which is triangle free,
Okay.
so it has every edge is a maximal clique now.
Okay. So it right. So okay. So I said that MEC of a DAG without V structures is caudal, and
Right.
I think if it is triangle free, then it must be a tree.
Oh, okay. Got it.
Because there can be no no cycle of length greater than 3 without a chord.
Okay, so that, yeah, like my confusion was that R could be more than N, right? Like if you look
Yeah,
at,
yeah,
so
in
if you
general,
remove
yes.
the V structure property, I guess what you could have is that, so it's like the N minus R quantity is delicately linked to the fact that you're dealing with chordal graphs.
Yes, exactly.
Otherwise,
So
like
yeah,
triangle free graph R could be number of edges, which could be much more than
yes,
N.
right,
Yeah,
right. So but in chordal graphs, R is always less than or equal to N.
got it. Okay.
It is also known, it was also known earlier. Uh,
Huh.
right. And yeah, now I'll continue. So I'll now define something called blocks in topological ordering. So let's consider a topological ordering sigma of D. D is again a DAG which does not have any V structure. Okay, the set of nodes that occur in sigma before or at the same position as a sync node, but strictly after the last sync node form a block. So I'll illustrate this with an example. Okay, so consider this DAG and the topological ordering A, B, C, D, E, F. Okay, so now we have seen that for this DAG, the sync nodes are B, E, and F. Okay, so now the blocks would be, so I said the set of nodes that occur before or at the same position as a sync node, but strictly after the last sync node form a block. Okay, so B is a B is a sync node, therefore AB is a block, and then E is a sync node, therefore all the nodes occurring after B are C, D, and it must be before or same position as a sync node. Therefore, CD is a block and F is a block. Okay, so this uh, so blocks are partitioning our topological ordering, right? So AB is a block, then CD was a block, and F was a block. It depends on the actual topological ordering and the set of sync nodes. So I hope this definition is clear. Uh, right, now I'll move. Okay, now, now I'll illustrate the definition of clique block shared parents orderings, which is our main technical contribution and is also the main ingredient to prove our lower bound. Okay, so a topological ordering sigma is said to be a CBSP ordering if it satisfies the following properties. First is something called a clique block property. So what does it say? It says that the subgraph induced by each block of sigma in D is a clique, is a complete graph, right? So we say that topological ordering sigma satisfies the clique block property if the subgraph induced by each block of sigma in D is a clique. Okay. And the second property is the shared parents property. So what does it say? It says that if A and B are consecutive nodes in sigma, and are in the same block, then all parents of A are also parents of B in the DAG. Okay, let me give an example. Okay, so again the same DAG. First consider the topological ordering sigma prime A, B, C, D, E, F. Okay, so now in this case the the sync nodes are B, E, and F, and therefore the blocks are A, B, C, D, E, and F. Okay, now consider this block C, D, E. In the graph, we can see that C, D, E is not a clique. Okay, therefore this sigma prime does not satisfy the clique block property, because the subgraph induced by each block of sigma must be a clique if some ordering has to satisfy the clique block property. Okay. Next, consider the topological ordering sigma, which is A, B, C, D, F, E. Right. So now again, we can see that A, B, C, D, F, and E, they are all cliques. Therefore, this ordering sigma does satisfy the clique block property, since the subgraph induced by each block is a clique. Okay, but now we can see, okay, but notice that there is a parent of B, there is a parent of C, which is not a parent of D. So B is a parent of C, but not a parent of D. And C and D are consecutive in sigma, as well as they lie in the same block. So C and D are consecutive nodes lying in the same block. But they do not have but C has a parent B, which is not a parent of D. Therefore, this shared parents property is not satisfied by this uh, topological ordering sigma. Therefore, again, the sigma and sigma prime are not CBSP orderings. Okay, now consider tau, which is A, B, C, E, D, F. Now again, the maximal, the sync nodes are B, E, and F. Therefore, the blocks are A, B, C, E, and D, F. And we can see that AB is a clique, CE is also a clique, and DF is also a clique. Therefore, this tau satisfies the clique block property. And let's see the parents of AB. So there is no parent of A, which is not a parent of B. And similarly for CE, C is a parent B, but B is also a parent of E. So this block is also fine. And finally DF, D has a parent C, and C is also the parent of F. Therefore, we can check that this tau also satisfies the shared parents property. Therefore, we conclude that tau is the CBSP ordering. Right. So, so this we will use the CBSP ordering in a main proof of a low bound, and it is defined in the following way, which I just described. Okay, so if there are questions, okay,
No, makes sense. Yeah. So
okay,
it's a
okay, sure.
special. It's a topological ordering that, in addition, has these properties P1 and P2.
Yes, exactly. Yeah.
And as of now, it's not obvious that such a, like, yeah, like every, even in caudal graphs, whether such a topological ordering exists. But I guess the punchline, you like the okay.
So I'll actually provide a sketch why such a topological ordering exists later. And yeah, so okay, I'll continue and provide that sketch. Okay, so before that, let me provide a summary of our results. Okay, our first result is a low bound, as I described earlier, and which is that, so which says that any set of atomic interventions or single node intervention that learn all edges of a DAG D without V structures must be of size at least ceiling of n minus r by 2. Here again, n is the number of nodes and r is the number of maximal cliques. Next result is a upper bound, which says that there is an intervention set I of size n minus r that can learn all edges of D. Okay, this also shows that a lower bound is tight up to a factor of 2, because n minus r is like less than or equal to twice of the lower bound. Okay, so to compare with Squares et al.'s lower bound, we show that uh, n minus r is greater than or equal to omega minus 1. Omega is the size of the maximum clique in caudal graphs. And again, this proves that a low bound is at least as good as the one by Squares et al. So I'll not go into the proof of this in the presentation, but we show this as well. And clearly this also means that n minus r is greater than or equal to 0. So in caudal graphs. Okay, so we, through some experiments, we also compare a low bound with that of the Squares et al. And we see that it is often significantly better. Okay, so now, as I said, I'll discuss the proof of existence of CBSP orderings and DAGs without V structures. Okay, so the first step is to show that DAG D, which is without V structures, has a topological ordering satisfying the clique block property. So this can be shown from well-known ideas in this literature of caudal graphs, and I'll not go into the proof of this. Please check a paper if you are interested. But yeah, so main part is to prove that that there is an ordering so if there is an ordering that satisfies the property P1 or the clique block property, we show that there must be an ordering which also satisfies the shared parents property or property P2. Okay, so now I'll go into how we prove that there is an ordering which satisfies property P2 as well. Okay, so consider the set of all topological ordering satisfying the property P1 and call it O. And clearly, if we have already shown that there is a topological ordering satisfying P1, O must be non-empty. Okay. Okay. So we will basically try to prove that there is an ordering with satisfying property P2 using contradiction. So again, assume that there is no sigma in O satisfying property, satisfying the shared parents property or P2. So what does it mean? This means that for any sigma, there is A and B such that A and B are consecutive in sigma and lie in the same block. And there is a parent of A that is not a parent of B and D. That is like if that is like a negation of shared parents property. So there is an ecom because clearly sigma does not if sigma does not satisfy the shared parents property, then it must be the case that there is an A and B that are consecutive as well as lie in the same block, and there is a parent of A that is not a parent of B. So and again, so among all such pairs of A and B, take the one with the smallest index in the topological ordering, the leftmost A. Okay, with the smallest value of sigma A. Sigma is A is just the index of A in the topological ordering sigma, and define FA equals sigma A. So A, we select the pair which such pair which does not satisfy the shared parents property with the smallest index sigma A, and define a function fa equals, sorry, this is f of sigma. F of sigma equals sigma of A. Right. Now, since O is a finite set, there is a finite set of topological orderings. They are countable. They are finite. And since O is a finite set, there must be some topological ordering for which f of sigma attains its maximum value, right? So sigma is a finite, O is a finite set, and therefore there must be uh, some ordering for which f of sigma is maximum. So this, so the idea now is to show the existence of another topological ordering in O, which for which f of tau is strictly greater than f of sigma. This will complete our proof, right? So now I'll describe the how to given sigma which attains given sigma for which f of sigma is maximum. We will construct a tau for which f of tau is strictly greater than f of sigma and therefore obtain a contradiction. And again, f of sigma was defined to be sigma A, where A comma B is the pair with the smallest value of sigma A, and A comma B says that the parent of A is not a, there is a parent of A that is not a parent of B.
Hi, Vibhor.
Yeah.
Just one comment. We are at 1 hour now. So if you can wrap up in the next 10 minutes, 5-10 minutes or so, it'll be great.
I see. Sure. Okay. Now I'll describe this construction of tau. Okay. So define this set CA to be A union parents of A, SA to be the set of all nodes for which CA is a subset of their parents, and let f of sigma, which was also sigma A, to be some number j. Okay, so let this YA be the set of nodes that are after A in sigma, but not in the set SA. Okay, so now I'll show how to construct this tau. So first J nodes, keep them same as sigma. First J nodes in tau are same as sigma. After this, the nodes in SA appear according to some topological ordering of the induced subgraph restricted to SA, and that's satisfying the property P1 or the clique block property. So this can be obtained because there is always a topological ordering satisfying the clique block property in DAGs without V structures. Finally, the nodes of YA appear according to their ordering in sigma. I'll just give a small example to better illustrate this. Okay, consider the same DAG and let sigma was this A, B, C, D, F, E. And we can see that sigma does satisfy the clique block property since all the blocks induce a complete graph. So AB is a complete graph, CDF is a complete graph, and E is a complete graph. Okay, but B is a parent of C, but not a parent of D. Therefore, we can see that CA should be B comma C because it is the set of all parents of C in this case. So CD is a pair A comma B. So C, the parents of C are just B and B, and therefore CA becomes B comma C. And SA is the set of all nodes for which CA is the subset of their parents, and we can see that E has parents B comma C, and therefore CA is a subset of parents of E, and therefore SA becomes just E, and there's no other node satisfying the same thing. And Y is the set of nodes that occur after C but are not in SA. So therefore YA would become D comma F. So finally, what would be tau? Tau would be we take all the so till the first J nodes, it would be same. Therefore, A, B, C, and finally we take the nodes in SA in some topological ordering that satisfies P1. But since this is a single node, it would be just E. So therefore, it becomes A, B, C, E, and now the nodes in YA appear according to their ordering. So therefore, the final tau becomes A, B, C, E, D, F, and we prove that tau must satisfy the shared parents property as well. Therefore, we obtain a tau which is this F value greater than sigma, which in turn is a contradiction. So this was a sketch of the proof of existence of CBSP orderings. Now, I'll quickly provide a sketch of a low bound. So we see that there must be a topological ordering which satisfies the property P1 and P2. Therefore, a CBSP ordering must exist. And take any two nodes lying in the same block. So we show that if there is an I which does not intervene on A nor on B, then I cannot orient the edge AB. Edge between A and B, and there is an edge between A and B because they are in the same block and therefore are part of a clique. So which this finally using this step 2, we would obtain that the size of I is greater than or equal to the quantity shown here, where this mod Li sigma is the size of the ith block. So manipulating this, we finally will arrive at a low bound. So the main idea was this existence of CBSP orderings and showing that if there is an intervention set that does not intervene on two consecutive nodes of a block, then the edge between A and B will remain unoriented. Okay, so now the upper bound, which is just the simply we show that the V minus S, where S is the set of sync nodes, is an intervention set that can orient the MEC of D if the true DAG was D. Okay, therefore, and clearly the size of I star V minus S is N minus R. This means that a low bound is tight up to a factor of 2. So for example, in this graph, I star would be ACD because B, E, and F are sync nodes. Therefore, and just to verify, it is less than twice of N minus R by 2. Okay, so now we also have some extension of our results to multi-node interventions where an intervention can simultaneously randomize more than one node. So first result is that we show that a single intervention is sufficient to learn a DAG for the case when an intervention can simultaneously randomize up to n nodes. This means if you are allowed any size intervention, then only a single intervention is sufficient to learn all the edges of a DAG. And we obtain a lower bound that is tight up to an additive factor of r by k for the case when each intervention can simultaneously randomize at most k nodes, where k is some number. Okay, some future directions are to design a causal graph learning algorithm with an approximation guarantee on the number of interventions with respect to the lower bound, and understanding the power of interventions in the setting where latent variables are present. So these were the references, and thank you.
Vibhor, I had one question. So that the assumption, or not really an assumption, you mentioned that the graph, the baseline graph is caudal. Like, what was the reason for like assuming that?
Okay, so it turns out that it, that the MEC of DAGs without V structures is caudal, and and even if you have a general MEC, okay, so then as I discussed, if you remove the all the directed edges, you will obtain caudal components, undirected caudal components, and uh, it is well known that if we intervene on node of a caudal component, it will not affect any other caudal component. So therefore, if we want to obtain a lower bound on the, let's say, number of single node interventions, then the complete lower bound would just be, so if you have, let's say, some k number of caudal components, then it would be the total sum of lower bound over those k caudal components. So if we just obtain an algorithm or lower bound for caudal MECs, it would generalize to arbitrary general MECs or arbitrary DAGs.
Okay.
And you can see this paper by Hauser and Bullman, 2014, to for details, and even our paper.
Okay.
Thanks, Vibhor, for the great talk. Are there any other questions?
Thank you.
Hey, yeah, we would like maybe one quick final thing. So in the upper bound, you're sort of assuming that you are given the
Yeah,
like. I mean, it's sort of uh, almost like
right,
a lucky
right.
intervention.
Yeah, exactly. It does not give an algorithm, but it says that if someone is very lucky, then they may orient and those n minus
Right.
r interventions.
Okay.
And
But
and yeah, but it does give the tightness for the lower bound because
true.
there is an intervention set that can
Yeah.
orient.
But in general, what is the like without like for the unlucky ones among
Right.
what is the
So there is so as this Squares et al. Paper has a
right?
upper bound for learn, like on the number of interventions for uh, learning a causal graph starting with just the MEC,
Uh-huh.
and and it so for some special classes of graphs they have a approximation factor of log of number of maximal cliques.
Okay.
So this means they require at most log of number of maximal cliques time interventions to learn
Mm.
a causal graph for some special category of graphs called intersection incomparable graphs.
Okay.
But in general, approximation factor is not known for for any general category of caudal graphs.
Right. And so like so it's kind of interesting that like for trees, right? Like you're effectively saying that I mean the chromatic number itself is like 2 or something. So that's a
Yeah.
you're saying one intervention does it for a tree. That's a very
No, no, no,
strong.
no, no. It says it log n. So in
Oh,
a tree, the number of maximal cliques is n minus one. So
okay, okay.
log n number of interventions can orient a tree.
Suffice. Okay, well, fine. Even that is sort of.
Yeah.
I mean, the lower bound is one, but and the no, upper bound is log n. So
Yes.
there
Yes.
is some scope of improvement there, even for trees.
So in trees, actually, if you consider the lower bound for algorithms, so this is a universal lower bound. This
Right,
means it would be valid for any intervention set. But
right,
in general, if you consider lower bounds for adaptive algorithms that
right.
that have a guarantee that no matter what the final ground truth DAG is, they will orient the DAG
Yes.
in some number of interventions. So there is actually a different lower bound. So which is something like log of n by d, where d is the maximum degree of the tree.
Okay, okay,
And so it is like there is some scope of improvement, but for trees, it is more or less.
set.
Log n is more or less tight
Okay, okay. Makes sense.
for
Yeah.
algorithms. Yeah.
For
This universal lower bound is just one. So yeah, we cannot.
right, right. Excellent. Thanks.
Yeah, thank you.
Hi, Vibhor. Actually, coming back to a question that Siddharth had asked at the start, uh, is there any scope for extension where, let's say, for where we have finite samples to check independence, or where there is no guarantee of independence?
Right. So I think even formulating the problem in that case is is not clear, right? So what we have thought a little bit about that. So for example, it may be given that using observational data, we have learned a MAC that has certain edges present with some probabilities. So we are given that the adjacencies are correct with certain probabilities. Then we want to learn the DAG, learn the directions using interventions. So of course there would be a lower bound again, and but it is not very clear how to formulate the problem exactly for that setting, and even whether this assumption is okay to say that each is there with certain probability.
Right. I'm guessing then you might not want to consider uh, MECs including grass, which have very low probabilities. So if there's a very low probability of a certain graph given the data,
Mhm.
you can just exclude that possibly and make the MEC for the rest and then carry out your procedure.
Right. So yeah, it's I think that makes sense, but it so currently, as as I show in the presentation, MECs have nice structure, which is caudal. Uh, like they are in general chain graphs with caudal chain components, but let's say caudal MECs are there. But now it may happen that this we cannot just say that the MEC starting MEC is caudal, and therefore many of the things will become hard. And I'm not like I can't say exactly what would be difficult there, but yeah, I think that problem is valid and important, but uh, yeah, I'm
But
not.
it's not,
I don't.
yeah.
I can't formulate it properly right now.
Okay, thank you.
Yeah, thanks. Thanks for the question.
Okay, if there are no other questions, I can end the recording here. Thank you, Vibhor, for joining us and giving this excellent talk on some of your work. Thanks again for joining all of you.
Yeah, thank you. Thanks, Rahul.
Thank
Thanks, everyone.
Hey, Vibhor, let me ask a question before
Okay.
you leave. So,
Yeah.
this existence proof that you identified, it's like a potential argument, like this function f keeps on improving till you get to it. Is it
Yeah.
constructive? That is like, say, I actually want to find this, like, can I do it in polytime or something? Because in causal graphs, like, for example, omega can be computed. Like, it's
Yeah. So I think you are asking, given a topological ordering satisfying the property P1, can we
right.
construct a ordering which satisfies property P2 as well?
Yeah, efficient, like in
Ye-
polytime or something.
Right. So I think the same construction I described would work in let's say at most. I think I'm not I haven't analyzed it, but clearly in
Right.
at most n steps it would work because
Okay.
we prove that f of tau is greater than strictly greater than f of sigma. So eventually it
Right.
would and it is polytime. Uh,
Okay.
yeah.
That's good. Okay.
Okay.
Yeah, quite interesting. Yeah, graph theory to causal. Huh?
Right, and I mean, I have been thinking about how the CBSP ordering is related to other well-known orderings. Like, so there is something called a Lex BFS ordering. So,
Hmm.
so if we can understand the relation among them, there may be better algorithms to obtain CBSP ordering. So, for example, I'm just saying if CBSP ordering is same as that Lex BFS ordering, then
Hmm.
there is known algorithms to obtain Lex BFS orderings. So
Okay.
then if we can prove that they are same, then we also obtain a CBSP ordering, right? So there may be better constructions to
And
obtain.
Lex like stands for something like lexicographic
Yeah,
or
yeah, lexicographic BFS.
okay. Oh, okay. Interesting. Anyway, thanks. Yeah, great talk. Thank you.
Yeah, thank you, thank you.